Is that fine?
Yeah.
Yeah.
Thanks. Okay. Yeah. So yeah, we're gonna resume. This is the last part of the lecture. We're gonna be talking about tokenization. So yeah, let's get started. As we mentioned, transmission and propagation of the signal leads to some imperfections, phase offsets, frequency offsets, all that. The relative motion of the two components, transmitter and receiver, will also yield some effects. For RAP, obviously that doesn't matter. We're not like taking our thing in a car or anything. But in general, there will be some frequency and phase offsets. In a kind of constrained environment, you can imagine also that there will be multiple reflections of the signal as it bounces off different things. So there's that. But yeah, three things we're principally concerned with are frequency, phase offsets, and then noise. Yeah, so I already discussed kind of how we end up with constellations like this. This corresponds to a frequency offset because we're basically just multiplying our received waveform with a time varying like phase. And then over there on the left, we just have a constant. So yeah, our first idea might be to compute like an FFT to determine the received frequency of our signal. Now, this is good because it lets us estimate the frequency, but there are a few problems with this, notably that if the frequency offset is not constant, then we don't have a way to actually track that offset. Number two, the FFT is kind of a long operation, so it introduces an additional time constraint. And the third and fourth, I guess, issues are number one, that we already have a rough estimate of the frequency, right? Because we know what the carrier frequency should be, we can just go based on that, and then we just need a way to estimate the error. And we still also need to determine the phase, which again varies with time, which is why an FFT recomputed a lot doesn't exactly help us. So our solution to this is PID control, pretty much. So yeah, the idea is basically just that we calculate an error, and then we adjust the output signal based either on that error, the accumulated error over time, or the derivative of the error with respect to some parameter. So yeah, just a few general characteristics about PID control. The proportional error is the main driving factor that gets us close to our reference point. The derivative kind of reduces overshoots and oscillations, and the integral controller is there to eliminate steady state errors, which in our case, again, is kind of important because you can think of, say, frequency offset as like a steady state phase error. That will probably actually make more sense in the next lecture, but yeah, I'll just put it out there for now. So our goal becomes something of, I guess, an optimization / PID problem, right? So we have this this phase offset, right, introduced by our channel, which we don't know. Then we have our two different carrier frequencies on the TX and RX sides, and yeah, we have this last parameter that we control. So this is an additional phase that we will add to our carriers on the receive side. So yeah, if we just do a bit of math, we can see exactly kind of what this looks like. So the complex baseband signal, what I'm doing, by the way, is just going through this diagram in a bit more detail. Wait, I skipped too far ahead. Which slide is it on? Here. So yeah, this is just our TX side passband signal. We multiply that by our time varying phase, and we get the complex passband signal, right? And then just substituting in our pole-shaped waveform, then the carrier from the modulation, then the channel phase gives us this result for the passband signal, right? And then when we demodulate, we multiply like this expression by this carrier here, right, which exists on the receive side. So we have the carrier frequency plus some error, basically, that we want to minimize. And so what that leaves us with is the signal here. We're also applying, by the way, the phase that we control on the receive side. So that leaves us with this signal here, right? And ultimately what that simplifies to is our hole-shaped TX side waveform multiplied by some time varying function that captures both frequency and phase offsets, and then we have the phase that we control. Any questions about this though? Okay. So yeah, if we, again, the nice thing about complex baseband is just that it lets us really easily recover the I and Q components from expressions like this. So if we actually do that, then we get a received I component here and a received Q component here. So in general, who can tell me kind of what happens if I don't know, what Greek letters are these? It's like phi theta. If phi and theta are not equal, then what do we have? Like what's actually happening to our signal? You don't have to overthink this. It's just like, what should we get versus what do we actually get? So in general, or all we want really, right, is for our received I component to equal x of I by itself. And similarly, yq should just equal xq by itself. If theta and phi are not equal, then some of the q component of our transmit signal will leak into the I component, and the same thing will happen here. So some of the I component will leak into the q component. Now this actually tells us basically the algorithm that we're going to use to derive like the this tracking mechanism that we'll use. But all we want to do, right, is get theta to match phi. Then this component vanishes, the q component vanishes here, and then the I component vanishes here, right? And then all we're left with is x sub I for y sub I, and x sub q for y sub q, which is exactly what we want.
Wait, sorry, can you clarify what phi and theta are again?
Yeah, sure. So I'm going to go to this diagram here. So the frequencies are in general different, transmit receive side, and then we're going to have some effect from the channel itself. So all phi is a function that captures both this frequency difference and the phase difference from the channel.
And theta is?
Theta is a parameter that we control. So it's just a phase that we generate based on yi and yq.
Okay.
Yeah. Okay, yeah. So what we're gonna want to do, right, is make theta match phi, which has the result of making y sub I equal to x sub I. Now remember again that if we are using VPSK, what should the q component be? It should always be 0, right? And similarly, our in-phase component should always be either 1 or -1 when we sample, because those are only two symbols. So what we're going to do is basically just square the received I component, and we want to maximize that thing, right? Because we know that unless something has gone terribly wrong, the I component should always basically be kind of in a known range, roughly -1 to 1. And when we sample, get a symbol back, right? If I go back to the constellation, it can be like kind of anywhere in the middle. So we want to maximize it and bring it as close to 1 as possible. Yeah. Okay, so I'm going to borrow a concept from ML here as well, just gradient descent. All we're doing here pretty much is calculating some error loss function j. Then we're going to calculate exactly how it changes with respect to theta, right? Because theta is the parameter that we control. So if we say, okay, we change theta from pi to pi plus 1, 0.1, then if we see that j blows up, then we say, oh, we did something terribly wrong, so we're going to adjust theta in the other direction and so on. So basically, by iteratively modifying j, we're able to find some sort of minimum in our loss function, which is exactly what we want, right? That's done step by step as we receive new samples. Does that process kind of make sense to everybody? Yeah, so this is just our update rule. Alpha controls how big we change theta for a given change in our error function. Okay. So yeah, there are a bunch of steps here, so I'll kind of break down each one. We've defined our error as basically the I component squared, right? One thing actually that I did mention is basically that if we reach a minimum, then the gradient of j is going to be 0. If you reach a maximum, the gradient is also going to be 0. So that's kind of what we're trying to get at here. But yeah, so if you just take the expression for j and write it all out, then this is what you get. If you take the derivative with respect to theta, then you get this expression here. I'm not going through the steps, I just listed them here. And by some coincidence, if we multiply the received I and q components, you get the exact same thing. Now the reason why that's important, right, is because theta is the output from some system that we define, right, some function. And if we calculate the gradient of j, then we need to keep track of j, all that. This gives us a very easy way to compute this value that we're interested in, right? So we just take our received samples, which we filtered, multiply them together, and then that gives us basically the parameter that we use to control which way we shift data. This also tells us basically what the block diagram we're going to use for our system is, which is over here, right? So again, we get our passband signal over there on the left, then we demodulate it, we filter it, and then from there we get our IQ components, multiply them together, and we get some data that we then apply to our carriers. And then we just repeat the process. So ideally, actually, kind of interesting fact, this is supposed to be done like sample by sample as we receive each new sample. The actual RAP system does not work that way because the MCUs are not fast enough to do that. I think when Nat and Daw measured it a couple years back, it was like hundreds of times too slow. So the way that we actually do this in RAP is basically on the transmit side, we transmit the same sequence over and over again. And on the receive side, we just take a very large buffer, twice the length of the message that we know, and then we just read and sample, so that way we know our message exists somewhere in that range. From there, we just do all this processing without worrying about anything that's coming in at any given time. So, yeah, the RAP system isn't exactly real time, but don't tell anybody. But yeah, you can see that on the next slide. If we kind of combine the two concepts that we talked about, then you can see exactly how the update rule for data maps to the PID controller that we're talking about, right? Because we've directly computed kind of this error, which is the IQ components multiplied together. And if we keep track of how that error changes over time and the accumulated values, then we can create a PID controller that we use to update data. So that's most likely going to be what your second module is going to be about. So stay tuned, I guess. That'll be released before the end of the quarter. And yeah. Are there any questions about Costa's loop? I don't know if I named it yet. We were talking about a Costa's loop.
Can you just explain, like, conceptually, I guess? So, like, we have an error function of, like, how good our guess data is, basically.
Yeah.
But we don't actually know what phi is.
Yes, that's correct.
So how does it make sense that we're able to, like, match our data up to something?
So good question. The reason is basically that the nice thing about this method is that we don't actually care necessarily what phi is, because the kind of error is encoded in the IQ components themselves. So, right, if theta and phi are different, then that's going to show up in y sub I, and similarly with y sub q. So if you make an error function that depends on IQ, then the difference in phi and theta is also going to be like propagated through to that. So actually the formulas, by the way, this is all specific to BPSK. So there will be different like error formulas, different update rules for QPSK and so on. This is just one that works for BPSK.
So it's also kind of dependent error on x, like knowing xi and xq, but it just so happens like yi.
Yeah. So again, just the reason for that was because of this fact here, that if we take the derivative of j with respect to theta, then it comes out to be exactly the same thing as if we multiply the IQ components. That's why we're able to use this as the like derivative function. Yeah. So actually, I guess one like sanity check that you can see is that if the q component is 0 as it should be, then well, the filtered q component, if that's 0, then this is also 0, which we want. Yeah. Yep.
Wait, so does this mean that like earlier on there's more likely error? Like, does it need time to like update a better data?
Good question. The answer is yes. Yeah. So that actually reveals an interesting question, which is that the maximum kind of, let's say we're running at the same frequency, the maximum phase difference we can have is, let's say, 90 degrees, right? So if you draw a constellation for that, again, assuming that we have for now just a phase offset, which our Costas loop can handle, we're gonna end up with samples here and here, or like sample symbols, right? We want them to be here and here. So now the question is basically, if we just use the Costas loop, right? Is there any guarantee that this constellation will swing the right way? Let's say that this is supposed to be a 1, right? And this is supposed to be like a -1. Then we want this symbol to map here, and we want this symbol to map here. Is that guaranteed with the Costas? No, exactly. Because all we're trying to do is maximize the in-phase component, right? It can't differentiate between a 1 and a -1, which means that we can end up with a situation like this. And this just means that all of our symbols will be, how do I say this, wrong. Yeah, so we'll end up with 100% error rate. So we'll see next time actually how to fix this, but yeah, this is just one problem to be aware of with the Costas loop. But yeah, are there any questions about anything I'm talking about? Okay. Yeah, then that's actually it that I have for this lecture. To kind of recap, match filtering helps us minimize the noisy part, right? Maximizing the SNR just means maximizing the part of the signal that we care about on the receive side. And then the Costas loop, which we talked about, helps us correct for both frequency and phase offsets. And there are a number of problems that we have left to solve. Actually, the one I just described is not listed here, so 3 problems. One is that we can end up with a situation where the Costas loop blocks kind of the wrong way, and we end up with a 100% bit error rate. So that's one problem. The second is that the demodulated I and Q components themselves will have slight I and Q phase differences and frequency differences. You can kind of think about this as just like if you have like the demodulated waveform filtered and everything, then you should just have like your message pole-shaped waveform. But that itself can be distorted as well. So that's something that we're going to need to account for, because when we sample, right, if we sample at a constant rate, but the signal is distorted, then we're going to end up with the wrong sequence. And then the other problem is that we don't actually know where the message starts. So all of this discussion has assumed that we know exactly when to start sampling once we've demodulated our signal. So that's yet another problem that we need to discuss, which actually is very relevant for this problem now that I think about it. But yeah. Does everyone understand what the problems remaining are and what the problems we solved are? Mm-hmm.
I don't know if you already talked about this before, but how do we guarantee that it's not more than 90 degrees phase offset?
Well, the reason why it's the maximum of 90 degrees phase offset is because you can just think about it as if you rotate that a little bit more, then it just becomes like less than 90 degrees from the other side.
But it's like really wrong then, right?
If it's really wrong, then we end up with a situation where, again, it locks on kind of to the wrong like symbol. So each symbol will map to the other symbol.
Yeah.
Yeah, for lack of a better way to describe it.
Can you explain why these two problems happen again?
Yeah, sure. So actually, I'll draw this out because it's easier to do it that way. Ideally, once we've filtered and demodulated our passband signal, we should end up with a pulse shape, let's say for the I component, that looks something like this, right? And we know on the receive side that, okay, like our symbols are supposed to be here, here, like this, right, so on. But now if there's some distortion with the signal itself, then this is not guaranteed, right? So we can end up with like these two are too close together, and then like, basically, I don't actually know why I just drew the same waveform twice. I can illustrate it with just one. But let's say that we sample here, right? And then the next sampling period is right here. And then this one is over here, and then over here, over here. So now the problem is that over time, this error can build up. We're probably gonna sample incorrectly, right? In general, that's not a good thing. So we're gonna see next time basically different algorithms that say, okay, if we sample at this point, then we can use data points around here to estimate, okay, should I increase the jump or should I decrease the jump? So then I can, let's say, decrease the jump in this case, and then increase it again, increase it, and so on. Yeah.
Is that like phase and frequency offset is caused during like which step?
That would be, so this is an independent issue to the one I mentioned, right? So the issue I was describing happens, so the issues that we just solved are with offsets here, with the carriers themselves. Now we're basically describing the issues that can happen if our sampler, like if our sampling method is incorrect. If we, like, for example, we should end up with like a waveform that's very nicely spaced. Its samples are all like let's say 50 samples apart, right, in time. When we actually transmit that, that's not necessarily guaranteed on the receive side, even after demodulating, correcting pairs and so on. Yeah. That's because of the other issues I mentioned, like noise, and then channel effects. Yeah. Yeah. Good questions. Yeah, thanks for attending once again. And see you next week for work sessions. Yeah.